Okay, please have a seat. Let us start. So remember, on Monday we saw something called Cauchy principle of argument. It was something like this. We start with a contour in S-plane. Okay. So here we start with a contour in S-plane. So this contour is something like this with some direction. Let us always use clockwise directions. So here we start with a contour in clockwise direction like this, and we call it gamma S in S-plane. And then we have seen that if we transform this contour, f of s, and this is a rational function in general, and no zeros or poles of f of s are on this curve, and we transform each point on this contour into f of s plane. So I have real f of s, imaginary f of s here, and then we transform that contour, we obtain something else. This is gamma f of s contour. Okay? And when we make this transformation, we then define something related to number of zeros and poles of f of s encircled by this contour, and the number of encirclements of origin by this contour. Okay? We have defined n as the number of encirclements of origin by gamma f of s. Okay? And we define z as the number of zeros of f of s encircled by this gamma s. Okay? And we have defined p as the number of poles of f of s this time. Poles of f of s encircled by gamma s. Okay? And then we learned something called Cauchy principle of argument, and this related n, z, and p using this expression. Okay? It has this expression. This curve will encircle the origin in clockwise direction by n times, which is going to be equal to z minus p. Okay? And here, by looking at the zeros and poles of the f of s encircled by this thing, we can know how many times this is going to encircle the origin. And then we have applied this theory to systems, feedback systems. So when we have a feedback system in the form g of s, h of s here, given like this, and if this g of s, h of s is given as a parameter k times n of s divided by d of s. Okay? And then we do something like this. We choose our original contour as a semicircle which has infinite radius. Okay? This is called the Nyquist path. Not Nyquist plot. This is Nyquist path. And we choose our transformation f of s as n of s over d of s. Okay? That is the specific way we choose our transformation. And then we plot something in n over d plane. This is real n over d, and this is imaginary n over d. And we draw our plot, and this is called the Nyquist plot. Okay? This is gamma n over d. This is called the Nyquist plot. And then what we do is that we define n as the number of encirclements of the point minus 1 over k. Okay? In this case, we are not looking at the number of encirclements of the origin anymore, because we are drawing the curve n over d But remember, at the beginning of this analysis, we chose our f of s as 1 plus k n over d. But this transformation was dependent on k and we didn't like it. And that is why we draw only n over d curve, which is called the Nyquist plot. And then we look at the number of encirclements of the point minus 1 over k by gamma n over d. Okay? And we define z as the number of closed loop poles encircled by, this is my gamma s, okay, by gamma s. This is at the same time number of unstable poles, number of unstable closed loop poles. Okay? And we define P as the number of open loop poles encircled by gamma s, or this is at the same time number of unstable open loop poles. Okay? We have derived this why these are selected like this, and we have seen that n is equal to z minus p. And here in Nyquist stability analysis, we are interested in z, which is the number of unstable closed loop poles. So z is given as z is equal to n plus p, which means that if this z is a positive number, the closed loop system is going to be unstable, and or if this z is equal to 0, the closed loop system is going to be stable. This is a very short summary of what we have done in the previous lecture. In this lecture, we are going to solve one more example. We are actually going to be solving 3 examples in total. We already solved the first example, the easiest one, in the previous lecture. In this lecture, we are going to make it slightly more difficult. And in the last example, it is going to be the ultimate Nyquist plot example that we can draw. So here, let us look at an example. So let us say that we have the following system. So I have K, and I have G of S, and I have H of S here. Here this GH, G of S, H of S, is given as 1 over S, S plus 1, and S plus 2, given like this. Okay? And the task is apply Nyquist stability analysis or Nyquist stability criterion for when k changes between minus infinity and plus infinity. Okay? So we are now going to draw the Nyquist plot, and then we'll try to make a stability analysis for different k values. So now let us try to see what we are going to do. The first thing that I'm going to do is that I will actually draw my Nyquist pad. Okay? The Nyquist pad is a semicircle which actually encircles all of the right half plane. Okay? Open right half plane is given like this. And now I'm going to actually mark the open loop poles and zeros here. So the poles are here. Okay, minus 1 and minus 2. Here, in general, when you have a transfer function given like this, n of s over d of s, if the system has a 0, if n of s has a root on the contour, it is not going to cause any problem to us. Why is that? Because in the original Cauchy principle of argument, if there is a 0 of the system on the contour, then your transformed contour would pass from the origin. Okay? And then you wouldn't be able to find the number of encirclements of the origin in that case. It's going to cause a problem. A 0 is going to cause a problem. And a pole is also going to cause a problem. Because in that case, the transform plot is going to go to infinity, and going to infinity is not a problem per se, but what is problem for us is that we won't know its angle. When it goes to infinity, if you have a pole on top of the original Nyquist path, in that case, the plot would go to infinity, but I won't know the angle of that plot. So it's going to, so both pole and the zero would cause a problem in the case of a classic Cauchy principle of argument. And the zero is going to cause a problem because I will not be able to find the number of encirclements of the origin when the contour passes from zero. Okay? But here, if I go back to how we are actually going to be using the Nyquist plot, is that I am almost never going to be interested in the number of encirclements of the point 0 here anymore. I will be interested in the number of encirclements of the point minus 1 over k. Okay? So that is why if this transfer function has a 0 on the Nyquist path, I won't care. It won't cause me any problem because I will be wondering about the encirclements of other points than 0 here. Okay? Minus 1 over k. And when is minus 1 over k is equal to 0? When k is infinite. So only for k going to infinity, which I won't usually care, I will be interested in the encirclements of the point 0. Okay? That is why a 0 of the transfer function here will not cause us any problem. But a pole is always going to cause a problem. And here we see that there is a pole of the transfer function on the Nyquist path. Okay? This is a problem because here, when the contour passes from this point, then the Nyquist plot is going to go to infinity. But in a complex plane, there are infinitely many infinities at different angles. Which angle at infinity it's going to go, I won't know. Okay? That is why, in such a case, I can't use this Nyquist path anymore. Okay? I have to modify my Nyquist path such that no pole of this transfer function would be on exactly on that Nyquist path. Okay? Here we do our modification in the following way. As I told you, the Nyquist plot going to infinity is not going to be a problem for us. It can go to infinity, but I want to know the angle it goes to infinity. Okay? When a pole is exactly on the Nyquist path, the plot is going to go to infinity, but I won't know its angle. That is why I'm modifying this Nyquist path slightly so that the pole is no longer exactly on the path, but we are turning around that pole on an infinitesimal circle like this. Okay? So this is called a modified Nyquist path. And we are going to do this if there is a pole of this transfer function exactly on the Nyquist path. If there is a 0, I won't care. It's not going to cause any problem because I'm looking for the encirclements of other points than the origin. So now comes the more difficult path. So here, if you look at this contour, then the radius here of this circle is infinitesimal. So I will call it as an epsilon. And the radius of the larger circle is r, and it's going to go to infinity. So here r is going to go to infinity, and epsilon is going to go to 0. And now we are going to draw the Nyquist plot for this system. Okay? That is why I'm going to be transforming this contour by this n over d, n of s divided by d of s. I will transform each point on this contour by this transformation. I will take an s from here, and I will put it inside this transformation, and I will mark the same point on the n over d plane, real n over d, imaginary n over d. And I will draw something complicated here, and based on that complicated plot, by looking at the encirclements of different points, we are going to decide on the closed loop stability of the system. So now, how do we convert this circle or semicircle by using this transformation? The first thing that I have to do is to divide this contour into different parts. So I will call this point A, this point B, C, and D here. Okay? So now let us try to parameterize the curve over different intervals. I will first concentrate on the part from A to B. I'm going to transform part A to B into, by the transformation n over d. In the part from A to B, our S is epsilon e to the j theta. Okay? And here, we are on an infinitesimal circle. Epsilon goes to 0. It can be as small as possible as long as it's not equal to 0. And what is going to be the theta values? Theta is going to change from where to where? Yes? From 0 to 90 degrees, and it is going to increase while it's trying to do that. It's making a counterclockwise rotation. That is why I put an increase there. Okay? Now I'm going to substitute this parameterization into my transfer function. So let us write n over d is equal to 1 over epsilon e to the j theta, epsilon e to the j theta plus 1, epsilon e to the j theta plus 2 here. Okay? Now, since epsilon goes to 0, here in these summations, these epsilon e to the j thetas are negligible. Okay? I won't care about this. These are 0. Okay? So I can write the resulting complex quantity as 1 over 2 epsilon. There is a 2 coming from here. E to the minus j theta here. Okay? And I can write the same thing as the r times e to the j phi here. R is equal to 1 over 2 epsilon, and r goes to infinity. Okay? And then I have phi, which is equal to minus theta. Phi is going to start from which angle? Phi is equal to minus theta, and it's going to start from angle 0, and it's going to end at minus 90 degrees. And it's going to go from 0 to minus 90 degrees, clockwise or counterclockwise. This is going, as you see, increases counterclockwise. So it is going to decrease because of this minus sign, meaning that it's going to go to minus 90 degrees in a clockwise manner. Okay? So this actually completes my analysis from A to B. So we see that this is the transformation from A to B is going to be approximately a circle which covers 90 degrees, an arc, an infinite radius arc, which covers 90 degrees, starting from 0 degree and going into minus 90 degrees. Okay? But we see here that the Nyquist plot is going to be at infinity. Okay? We are going to have an infinite radius circle, but we know that in this case the angles. Okay? We know which angles it would have. So now let us look at the most difficult part, probably, from B to C. From B to C, what is our parameterization? S is equal to j omega. So we have j omega, and omega changes from where to where? Omega changes from epsilon to infinity, and it increases. We always have a positive omega values. It's never 0 in this case. And let me try to substitute this. I can actually write this transformation as 1 over s cubed plus I have 3s squared plus 2s. I will substitute s equals to j omega there. So I have n of j omega, d of j omega. So what can I say about this part of the Nyquist plot? It is the frequency response of the open loop system. Okay? So if you know the frequency response without knowing the transfer function of the system, it's fine. By making experiments on your system, you can sometimes obtain the frequency response of a system. You can actually look at the amplitude and phase differences if you give the system some sinusoids, and then you can obtain this quantity experimentally without knowing the transfer function, actual transfer function of the system. That means that this part of the Nyquist plot can always be drawn by having this frequency response of the system without knowing the transfer function itself. But here we have the transfer function, so we can actually obtain something from this. So let me substitute here s equals to j omega minus j omega cubed minus 3 omega squared plus 2 j omega. And then I'm going to be concentrating on the real parts and the imaginary parts of this transformed quantity. And that is why I'm going to collect the real part, minus 3 omega squared, plus in j omega parentheses, I have 2 minus omega squared. And now this is a reciprocal of a complex quantity. It is difficult to interpret this quantity. That is why I want to make the denominator real and positive. That means that I'm going to multiply both numerator and the denominator by its complex conjugate of the denominator. So if I do that multiplication, I have minus 3 omega squared minus j omega 2 minus omega squared. And the denominator now becomes real and positive. It is 9 omega to the 4 plus omega squared 2 minus omega squared squared. Okay? Now I can easily interpret the real part and the imaginary part of this transformation. So now in order to be able to minimize my mistakes here, I'm going to make a sign table, okay, for real n over d and imaginary n over d. Okay? I'm going to look at some critical frequencies at which real part or imaginary part might be equal to 0. Is the real part 0 for some of these frequencies? For none of these frequencies, the real part is equal to 0. Is imaginary part 0 for some of those frequencies? Yes, for square root 2, we have imaginary part is equal to 0. Okay? This is a critical frequency where the imaginary part is equal to 0. So now this part represents omega going to 0, and this part represents omega going to infinity. Okay? So now let me put some signs here. The real part is always negative. And if I look at the imaginary part, what can you say about the sign when omega is smaller than square root 2? What is the sign in such a case? Yes? Yes, that is minus, and I have a plus. Okay? So here we have put the signs, and now I'm going to look at the extreme cases. What happens when omega goes to 0, and what happens when omega goes to infinity? As omega goes to infinity, both the numerator and the denominator would be dominated by the largest power of omega. What is the largest power of omega in the numerator of the real part? There's only one power. It's omega squared. Okay? And what is the largest power in the denominator of omega? It is omega to the 6. So that means that the real part is going to go to 0 as omega goes to infinity. And what about the highest power of omega in the imaginary part numerator? It is cubic power, so it is going to be smaller than the 6th power. That means that this is going to go to 0 as well. So now I will concentrate on omega going to 0. Okay? As omega goes to 0, the smallest power of omega is going to dominate both the numerator and the denominator. The smallest power of the omega in the real part is minus 3 omega squared. What is the smallest power of omega in the denominator of this quantity? How many omega to the 4?
Omega squared.
Convert somewhere.
Omega squared.
Yes, it's omega squared. How many omega squares? 4 omega squares. Okay? As omega goes to 0, this thing is going to go to minus 3 over 4. Okay? And if I look at the imaginary part, what is the smallest power of omega? Minus 2 j omega, and this is 4 omega squared still. Where is this going to go when you look at the imaginary part? As omega goes to 0, this is going to go to
0
minus infinity. So we see that the imaginary part goes to minus infinity. So now I'm going to evaluate the ratio n over d at the critical frequency. N of j square root 2 divided by d of j square root 2. In general, you can look any of these expressions and try to find the easiest one to substitute square root 2 for omega. If I take it here, for example, this term is going to be equal to 0, and this term is going to be 1 over minus 3 times omega squared is going to be 2, is going to be minus 1 over 6. Okay? And then finally, I'm going to be looking at the angle as omega goes to infinity of n of j omega d of j omega. Okay? So this is always related to the relative degree of your system. How many poles do you have more than zeros? Okay? So here, as omega goes to 0, s goes to infinity. Sorry, as omega goes to infinity, s would go to infinity, and I can approximate this transfer function as 1 over s cubed. And this is 1 over j omega cubed. Okay? And that actually means that the angle as omega goes to infinity is going to be what? What is the angle of such a quantity? Each of j omegas would bring us a minus 90 degree. Okay? And what is going to be the angle as omega goes to infinity for that ratio? Minus 270 degrees. Okay? So this actually completes this part, which is probably the most difficult part usually. And finally, I have the part from C to D. This part is easy. In this case, I'm going to cut this part short because usually this is going to shrink to the Nyquist plot is going to shrink to 0 at this part. And in this part, the parameterization is from C to D. We are on a circle with infinite radius, r e to the j theta. R would go to infinity, and theta would start from 90 degrees, and it decreases to 0 degrees. Okay? In this case, you really do not have to do much. We see that this s would go to infinity in that case. Okay? And that actually means that this ratio is going to go to 0. The only possible case where this ratio will not go to 0 is which case? Yes, there might be zeros more than poles. It usually doesn't happen in natural systems. So the only practically meaningful case might be when the number of zeros is equal to the number of poles. So, okay, in that case, this transfer function will not go to 0 anymore on this part of the Nyquist plot. So I have in this case n over d in this case would just converge to 0, and I can actually try to find details around 0 as I did in my first example in the last lecture, but I will skip those. Okay? So now we actually made all of the analysis necessary, and the only thing that I have to do here is to draw the Nyquist plot. So I will start here. This is my real n over d and imaginary n over d plane. Okay? So now I will start from point A. I will go from A to B first. So on A to B, I'm going to be on an infinite radius circle, okay? And the angles will start from 0, and it's going to go clockwise, decreasing to minus 90. Okay? So I'm going to be somewhere here, somewhere infinite here. This is going to be my point A, and we are going to go to the angle minus 90 degrees like this. This part of the Nyquist plot is at infinity. Why is that? It is happening because of the infinitesimally close pole here. Okay? It is going to go to infinity, and we are covering 90 degrees angle there. If this was square, for example, instead of s, if I had a square here, what would change?
The angles.
The angle would change. How much angle would I cover in that case? Double, 180 degrees. Okay? So the number of poles at 0 is going to determine how much angle you're going to cover at infinity in your Nyquist plot. Okay? So this is going to be my point B, 90 degrees. But here there is something tricky, because at the end of part from A to B, you're going to come to the beginning of this table. Okay? The beginning of this table is going to be saying that the real part should be minus 3.4, imaginary part should be minus infinity. The imaginary part is already minus infinity, but it says that the real part is minus 3 over 4. Okay? So here, there is something minus 3 over 4. Isn't this a contradiction? So the angle should be minus 90 degrees, okay, at the beginning, but This point, the beginning of this table and the end point of this analysis should be the same. The end point of the part from A to B is the beginning point of part from B to C. They should be the same point. What is going on here?
The angle as the point goes to minus.
Yeah, what is the angle of such a point? Minus 3.4 plus j omega so let me say j 1 over omega. As omega goes to infinity, no, this is not making sense. As omega goes to 0, what would be the angle of such a complex number? Yes? As omega goes to 0, what would be the angle of such a number? This is minus 3.4 is the real part, and imaginary part, let me say that it is going to be negative infinity. In that case, the angle is still minus 90 degrees. Okay, so there is really no contradiction here. I can ask you something even stranger. Omega plus j omega square. Let omega go to infinity. What is going to be the angle of this quantity? Sorry? It's going to be pi over 2. So you might actually think that a point with angle pi over 2 is going to have 0 real part. Do you think as omega goes to infinity, this complex number has 0 real part? It has infinite real part. Okay, so at infinity something strange can happen. Both the real and imaginary parts are infinitely different than 0, but the angle is 90 degrees. Okay, as omega goes to infinity. This is what is happening here. The real part is minus 3 over 4. Imaginary part is negative infinity. Yani aslında biz sürekli şuraların encirclement'larına bakacağımız için burayı eksi 3 bölü 4 göstermişsiniz, göstermemişsiniz çok önemli değil açıkçası. Sadece analiz yaparken böyle bir şeyle karşılaşırsanız kafanız karışmasın diye söylemeye çalışıyorum. Yoksa burayı ben eksi 3 bölü 4 burada göstermişim, göstermemişim çok önemli olmayacak en sonunda. Çünkü eksi 1 bölü k'nın encirclement'larına bakacağız. Okay? So that is not going to change much. This is not really that critical. So then we are at the beginning of this table, and we are going to remain in the quadrant where both the real parts and the imaginary parts are negative. So we're going to remain in this quadrant until we hit this critical frequency. Now we are drawing the frequency response part of the Nyquist plot, and we are going to remain in this part. At the end, where we have to go is this critical frequency, and at this critical frequency, we see that the ratio should be minus 1 over 6. So we're going to hit this number, minus 1 over 6. Okay? So then we're going to go from here to here. It really doesn't matter how you go there. I can draw something like this. I don't care. At the end, what is going to be important for me is the encirclements of the real axis. Okay? It really doesn't matter. I'm trying to draw the simplest thing that I can do here, where we have a convergence like this. And then I'm going to go into the quadrant where the real part is negative and imaginary part is positive. Okay, I'm going to get into this quadrant, and then I have to converge to 0. But I'm going to when we look at the Nyquist plot, we generally pay attention to how we converge to 0. Okay? And here, while we converge to 0, we have to make the angle minus 270 degrees. Okay? So here, if there was a 0 here, s plus 3, let us say, okay? In that case, what would be the angle that I converge to 0 with? It is going to be minus 180, because in that case, the transfer function at infinity would be looking like 1 over s squared. Each of the s's would bring me minus 90 degrees. That means that my angle would be converging to 0 would be minus 180. That means that when I converge to 0, I should converge from this side. But here, that angle is minus 270 degrees, meaning that I need to go to 0 from the top. Okay? So this is the first half of the Nyquist plot, and then I'm going to try to convert the rest of this curve, and these are going to be just the complex conjugates. Okay? So why is that? Because if this point is S, this point is S conjugate, okay? And into this transformation, N over D, if I substitute S conjugate into S, then this is going to be N over S, D over S, complex conjugate itself, okay? So why is this happening? Because we have real coefficient polynomials here, okay? If we didn't have real coefficient polynomials, this doesn't have to hold. And that actually means that I'm going to draw the symmetric part of this plot. So I'm going to continue from this point on, and I will draw something symmetric, and we will go somewhere like this, and I'm going to complete it like that. So now this is our Nyquist plot. Now we are actually ready to make a stability analysis. For that, I'm going to try to find -1 over k values, ranges for -1 over k, and I'm going to look at what would happen to the number of encirclements of -1 over k. For this example, the first thing that I'm going to do is to choose P. P is the number of open loop poles encircled by the Nyquist path. Open loop poles are at 0, -1, and -2. How many of them are encircled by this curve? None of them. So we have P is equal to 0, meaning that Z is going to be, which is the number of closed loop poles inside the encircled by the plot, Z is going to be N plus P. But since P is equal to 0, Z is going to be the number of encirclements of the point -1 over k. So the first thing that I'm going to do is that I'm going to look at the -1 over k candidate in this interval. So I will say that if -1 over k is smaller than -1 over 6 and between minus infinity. Okay? If -1 over k is in this interval, then k is going to be in this interval from 0 to 6. Okay? And what is the number of encirclements of -1 over k here? Draw a radial line and try to check what is the encirclement. So if you want to really spend some time, you can try to draw it like this. Okay? Wouldn't it give the same thing? Crosses like this, and the other one crosses like that, they cancel each other, and the number of encirclements is 0. Okay, so draw the radial line, anyway, from the easiest part. So here, N is 0, meaning that Z is equal to 0, meaning that we have 0 unstable closed loop poles, meaning that the closed loop system is stable for this interval. Now I will look at the other interval when -1 over k is between -1 over 6 and 0. In this case, k is going to be between 6 and infinity. Okay? And in this case, -1 over k is in this interval. How many times is it encircled? I'm just drawing something like this. I'm counting clockwise encirclements. So how many times do we encircle -1 over k? Twice. So I have here n, z is equal to n is equal to 2, meaning that we have 2 unstable closed loop poles, meaning that we have an unstable closed loop system. And finally, -1 over k can be in this interval, okay? So -1 over k can be between infinity and 0, and this is the case when k is negative, okay? And when k is negative, what is the number of encirclements? Again, you have opportunity to spend extra time by drawing it like this. Okay? It's going to give you the same thing. They're going to cancel at the end. They're going to cross that curve in different directions, and so this one is going to cancel this one, so you're going to end up with this one, okay? And it's going to be +1 in that case. And z is equal to n, in this case it is 1, meaning that we have one unstable closed loop pole. So what happens if this z turns out to be negative? N can turn out to be negative if it is encircling -1/k in the reverse direction, in counterclockwise direction, n can be negative. So what does it mean for z to be negative? It doesn't mean anything. It means that you messed up something in the calculations. It means that there is something in the analysis. There is something wrong. This z should never be negative. Okay, it's the number of something, so it shouldn't be negative. That means that in your analysis somewhere something happened. Yes.
Can we see something for the boundaries for the case?
Yes, the boundary in general, since we cannot determine the number of encirclements there, we won't be able to say anything about the boundaries. But But we know what is going to happen. For example, at the boundary 6 here, we see that two closed loop poles would cross the imaginary axis. Okay, we can actually say that there will be poles on the imaginary axis, and the closed loop system is going to be unstable there. Okay. So we have one unstable closed loop pole, meaning that the closed loop system is unstable. So the stability range for this system is just this one. Okay, when k is between 0 and 6. So here, in general, when we try to go around to open loop poles, we generally try to exclude them like this. Okay. So what you could have done, but it generally makes the Nyquist stability analysis a little bit more difficult. So I wouldn't recommend it, but instead of turning around the pole in that direction, you could have turned around from this direction. Okay, so you could have done that, and what would happen in that case? All of the analysis from B to C. So my neo A point would come here in that case, and all of the analysis from B to C and from C to D would remain the same. Okay, so all parts of the Nyquist plot which are not at infinity would remain the same. So here, these parts would still be remaining where they are. So here I have my -3/4 here and -1/6 here. These parts would remain there. So I have this. These parts would remain there, and the other parts, symmetric parts, would remain there. It would be something like this. Okay? The only part that is going to be changing would be the part at infinity. Okay? So let us try to look at what is going to happen. Now, when I try to look at A from A to B, S is going to be epsilon e to the j theta. Epsilon will go to 0. Sorry, epsilon will go to 0. That is correct. And theta is going to go from where to where? This is my new A point. Okay? Now, what should I say for the angle? It is going to start from 180, and it's going to go where? 90 degrees. It's going to go clockwise or counterclockwise? Clockwise. So it is decreasing, actually. I can actually say this. Okay? Now I can make the same analysis, and I can neglect these epsilon terms here. Okay? These epsilon terms are negligible, and I have exactly the same analysis. So only these angles will change here. Okay? These angles are phi is equal to minus theta. So phi is going to be minus theta. So we are going to start from minus 180. We are going to end at minus 90 degrees. Okay? And then it is going to increase or decrease. It is always the reverse of this thing because of this minus sign. This is decreasing, so this is going to be increasing. Okay? So I'm going to start here, minus 180 degrees, And in which direction should I go? Counterclockwise. So I have to go in that direction. Okay? I'm going to complete this like this, and the symmetric part of this thing is going to be like that. Increasing means counterclockwise, decreasing means clockwise. Okay? So this is going to be my new Nyquist plot. So I can now try to make a stability analysis, but of course we shouldn't expect to obtain anything new here. I need to obtain exactly the same results. So now what is P? How many open loop poles does this original curve encircle? 1. So in this case, P is equal to 1, and we have Z is equal to N plus P, meaning that we have Z is equal to N plus 1 always. Okay? And now I'm going to be looking at the encirclements. When minus 1 over K is between, I have here minus 1 over 6 and minus infinity. K is going to be between here 0 and 6. Okay? In this case, how many times in clockwise direction is the point minus 1 over K encircled? I need to count the clockwise encirclements, and in this case I see that the point minus 1 over K is encircled in counterclockwise direction once. What should I take my N? It is going to be minus 1. So here N is equal to minus 1, meaning that Z is equal to minus 1 plus 1, which is equal to 0, and the closed loop system is stable. Okay? And when you look at here, I have N is equal to 1, okay? 1 plus 1, I have 2 closed loop poles over this interval. And over this interval, I have 0 encirclements, meaning that I have 0 plus 1 unstable closed loop pole, which would make the closed loop system unstable. Yes?
And can you Nyquist effect cross a 0?
Yes, it can. As I told you, when it crosses a 0, then the plot is going to pass from the origin. And the plot passing from the origin is not a problem for us because we never check the number of encirclements of the origin here. We always check number of encirclements of other points. Okay? That is why it's not a problem. So here, for this example, if you look at the root locus, you're going to see something like this. Okay? So for small k values, closed loop system is stable. For large k values, the closed loop system is unstable. What is the k value here? It is 6. Okay? And the 6 corresponds to this point in the Nyquist plot. Usually, the most important point for us in the Nyquist plot is this point where the Nyquist plot crosses the negative real axis. And if you look at the root locus for negative k values, as I told you before over and over, this is not included in 302, but I can draw a root locus for negative k values. It's going to be looking like this for this example. And by looking at this root locus, tell me when the closed loop system is stable for negative k values. Never. It is never stable for negative k values. This is what we have found in our stability analysis. That's all for today. Thank you very much.
Buradaki encirclement'ı olarak nasıl?
Şimdi buraya geçiyorum. Bir tane line çiziyorum. Tamam mı? Şimdi bu line'ı kesecek bu arkadaş. Bunu clockwise mı kesiyor, counterclockwise mı? Şuraya parmağımı koyuyorum. Clockwise mı kesiyor, counterclockwise mı kesiyor.
Oradan bir tane var ama o line'ın sağa doğru.
Buradan bir tane var ama böyle counterclockwise